Hello everybody, my name is Aidan Maloney, and this is my presentation on an arresting cable for an aircraft carrier for the first project of control of automated systems. The first part of this project requires us to find the damper that will allow a 20,000 kilogram jet to land safely. The second part of the project wishes us to observe a much lighter aircraft landing using the same spring damper system. The third part of this project has us look at a new AAG system with a tunable damper for various aircrafts of different masses. For the first part of this project, the initial speed of the 20,000 kilogram aircraft will be 64 meters per second. The aircraft must come to a complete stop within 2,500 meters, and the experienced amount of G-forces on the pilot must be minimized for safety. For the second part of the project, the same spring damper system will be used, but this time the aircraft will only have a mass of 550 kilograms and have an initial speed of 35 meters per second. For the third part of the project, the distance ranges of a tunable damper will be found for each of the aircrafts used. The arresting cable was modeled and simplified, and the variables were made into equivalent values. The simplified model was broken down into 3 separate free body diagrams. These free body diagrams were used to write the state space models, and those state space models would be used to generate position, velocity, and acceleration data using Simulink. In Simulink, our initial conditions were plugged in, and our graphical data was generated. Here, we may easily view the position, velocity, and acceleration data that was just generated by Simulink. From the gathered data, we can see that the aircraft comes to a stop within 2,133 meters. Furthermore, the graphical model shows that the aircraft acceleration while coming to a stop has a maximum of -1.604 meters per second squared, which is easily survivable by any pilot. For the second part of the project, we try to visualize a lighter aircraft with a slower initial speed landing using the same spring damper system. Like before, we use Simulink to generate our graphical data. This time, though, rather than coming to a complete stop gently, this aircraft will begin to oscillate back and forth before coming to a complete stop. Because of situations like this, it makes sense that the Navy would switch to the new AAG system, due to the fact that its tunable damping ratio would easily allow various aircrafts to land safely. For the first aircraft, the KD may range from approximately 600 to 1,900 newton-seconds per meter. If the KD is less than 600, the aircraft will travel too far. If the KD is greater than 1,900, the aircraft will begin to oscillate. Using the equations found below, it was determined that the water drum distance has a range of 1.178 times 10 to the -5th meters to 3.73 times 10 to the -5th meters. For the second aircraft, the KD may range from approximately 8 to 300 newton-seconds per meter. If the KD is less than 8, the aircraft will travel too far, and if the KD is greater than 300, the aircraft will begin to oscillate. Once again, using the equations found below, the water drum distance range was determined to be 7.46 times 10 to the -5th meters to 2.8 times 10 to the -3 meters. This concludes my first project for controls of automated systems. Thank you all very much for watching.